Hi, in today's video we're going to be using the FDFD mode solver to calculate the electromagnetic modes on waveguides, calculate the change of the waveguide modes that are supported for different widths, as well as the propagation loss of waveguides through bands or through evanescent coupler, and see the coupling coefficients. So first, to access the documentation, we're going to be going to the GDSFactory .com website. Then we will go into the introduction, and then we'll go to the quick start. So as part of the quick start, we're going to be going through the GDSFactory Plus workshop, and we'll be using the SciEpic eBeam PDK. You can also use another one, but let's use the SciEpic eBeam PDK. So we have some videos here that will guide you through these simulations. So in the previous simulation, we've done it with an FEM mode solver. We're going to be accessing the workspace through this link, and we're going to be copying the user and the password. So from here, once you have done that, you will basically create a cloud workspace to do your work. In this case, I already created one before, so I'm going to be opening this one. And once you open the cloud workspace, you will have access to different notebooks, and we'll be using the notebook called Mode Solver FDFD. When you're running this notebook, you can I usually do Shift Enter, but you can also hit the play button. So you can see here you have the waveguide properties. So here this is a 0.5 micron wave waveguide at 1550 nanometer with a 220 nanometer thickness. And you can add things like a sidewall angle, as you can see here. Once you plot the waveguide, you can also simulate and compute the fundamental mode, which is the zero order mode. In this case, I'm plotting the EX field. You can also plot the TM mode, which is the first EY mode. And you can plot things like RIP waveguides or nitride waveguides, which have slightly different thicknesses or materials. Another thing you can do is you can sweep the waveguide width. Here it's very fast because I already ran it before. But you can see for these 220 nanometer silicon waveguides, the waveguide starts to be multimoded for T after like 0.5 microns. So another thing you can do is calculate the group index of the waveguide, where you calculate the group index for different modes, and then you can calculate also the loss of the waveguide due to the depending radius. So there's two types of loss. There's a mode mismatch loss because you're coming from a straight waveguide to a band waveguide, and there's also the radiation loss and the propagation loss through this band. So if you compute these losses for different radius, you can see that different mismatches, and you can also calculate the propagation loss as well as the mode loss. One good rule of thumb is that when the mode loss equals the propagation loss, that's quite a safe band radius to use, because if your loss is going to be dominated by the propagation, then it doesn't matter if you keep making it bigger and bigger. The radius, if you make it bigger, then it gets dominated at some point by the propagation loss. And yeah, you can see for waveguides, the bending radius is larger, and you can see this requires around 30 micron to get that bend radius in a safe spot. But yeah, we're going to be using fully edge waveguides for the course. This one is a waveguide coupler, where you bring two waveguides next to each other, and then you can simulate the different modes. And that's it. As you can see, the T mode, the coupling, there's different coupling lengths for T and TM. TM is the mode is less confined, so the coupling is larger. So you require less for a smaller gap. The whole light couples in less distance. And yeah, thanks for watching this video, and good luck at designing your chips. Thank you.